This is part 4 in our series of lectures on section 1.6. In this lecture we're going to consider proofs involving a more complicated array of quantifiers, and we're going to illustrate it by looking at an example involving limit of a function. I'm hoping that this can serve as an introduction to something that you'll see in more detail in your advanced calculus class, Math 315. So here you have the formal working definition of the statement that the limit of 2x plus 7 as x goes to 3 is equal to 13. So this is the formal working definition. You'll notice that it involves three variables, epsilon, delta, and x, each of them quantified, and it also has this conditional statement which depends upon those three variables. This notation for every epsilon bigger than 0 is a notation that's commonly used, and it's a shorthand for this here, for all strictly positive real numbers epsilon, comma, and what goes after that, of course, is the rest of the statement. And similarly, this notation here is a shorthand for there exists a strictly positive real number delta such that, and then after the such that, you just insert the rest of the sentence, whatever this means. So that's very commonly used, and you're going to see this used a lot in connection with statements about limits. So before we talk about how to prove it, let's begin by just simply reading what it says. So it says, for every positive number epsilon, there exists a positive number delta, such that for every real number x, if the absolute value of x minus 3 lies between 0 and delta, then the absolute value of 2x plus 7 minus 13 is smaller than epsilon. Now that's much more complicated than the proofs we've been dealing with up until now, but it's still the case that if you want to prove such a thing, you should read from left to right, and you should deal with each statement as you get to it. So you would begin by dealing with this statement, then this one, and then this conditional. Okay, so always read from left to right. Now let's try to understand a little bit what's being described here. We see this absolute x minus 3 smaller than delta. So the question is, what does absolute x minus 3 measure? Well, we can draw a picture of this. The absolute value of x minus 3 is just a statement of how far x lies from 3 along a number line. So if this is 3, and say x is here, then the absolute value of x minus 3 just measures this distance here. If x is on the other hand over here, then absolute value of x minus 3 is just this distance here. So in order that we have the condition that absolute x minus 3 is smaller than delta, it's telling you that if you take a little interval of radius delta centered around 3, so this distance here is delta, and this distance here is delta, then to say that the absolute value of x minus 3 is smaller than delta is to say that x lies somewhere in that interval. To say that it's bigger than 0 is just simply to say that x isn't going to equal 3. And we have a similar interpretation for this thing here. To say that the absolute value of 2x plus 7 minus 13 is smaller than epsilon is just simply to say that the number 2x plus 7 is within epsilon units of the number 13 on a number line. And so the idea of the definition is that no matter what epsilon is given to you, so it's sort of the epsilon is measuring how far from 13 you're willing to accept your 2x plus 7 should be. So no matter how small that tolerance is, you're able to find a delta so that if x is within delta units of 3, then this happens. In other words, by choosing x sufficiently close to 3, you can force 2x plus 7 to be within epsilon of 13. So that's the idea of what's being expressed here. So what is the first sentence of the proof? If you're reading from left to right, you would begin, as you've seen before, by saying, let epsilon be a given positive real number. Okay, then you get to this. You have to deal with this existence proof now, and we want to make it a constructive proof. So how do you respond when you want to prove something that continues like that? Well, you have to figure out how to choose that number delta. So essentially that's your task. You have to figure out how to choose a delta so that the rest of the statement works relative to the epsilon that was given to you and the delta that you've chosen. Now you don't have any control over the epsilon that was given to you, so you have no control over what that number epsilon is. So think of it as if you're in say a tennis match in which someone serves the ball to you, and it's your job to respond by returning the ball back to your opponent. You don't know, what it's going to look like until you actually get served the ball. So that's sort of like the epsilon that's been given to you. The epsilon that's being given to you is the challenge that's given to you by your opponent, and this is your response. This is your return of the tennis ball. Your response is you're going to explain how you're going to choose a delta that's going to deal with that epsilon that you were given. And it turns out the smaller that number epsilon is, the closer that epsilon is to 0, the more difficult it is for you to meet the challenge of telling us what the proper delta should be so that the rest of the statement works. Okay, so that brings us then to the ultimate aim of this lecture, namely for you to write a proof of this limit statement. So before you do that, let's look in a little bit more detail about the idea of how you would prove something like this. We'll do some calculations to see what's involved. Okay, so here's the statement. As usual, you read from left to right, so you're going to begin by saying let epsilon be a given positive real number, and then you get to the hard step. You have to explain how you're going to choose that delta, positive real number, for which all of the rest of this happens. So the calculation is going to involve us figuring out what is needed in order to choose that delta. But let's pretend for the moment that we have chosen it. So pretend we now have an epsilon and a delta. Now we say, what do you say when you see this? You say, let x be a real number. And now, let's say we do a direct proof of this. So then we say, suppose that absolute x minus 3 is bigger than 0 and less than delta. And then we have to prove that this happens. So what we're going to do is we're going to start from here and figure out what it's going to take to make that happen. And that will tell us how to choose the delta at the beginning of the proof. So let's calculate that quantity. We have 2x plus 7 minus 13. Now I'm not going to put less than epsilon, I'm just going to calculate this quantity out and see what it takes to make it less than epsilon. So that, if you look at it, that's 2x minus 6. We can factor out a 2 from that and get x minus 3. And now you get to something that's important. You get to a factor of x minus 3, absolute value, and we know that we're going to be choosing that to be smaller than delta. So regardless of how we choose our delta, this is going to be smaller than 2 delta. And so if I just simply chose my delta so that this was equal to epsilon, if I chose my delta that way, then this string of equalities and inequalities would say this is equal to this, which is equal to this, which is smaller than this, which is equal to this. In other words, this would have been smaller than this. We would be able to prove that. So there's the answer. It's telling you to choose your delta to be epsilon over 2, or you could choose it to be anything smaller than that. Any positive number smaller than that would work just as well. So now I think you're ready to go back and actually write the proof of this result. You're going to begin by saying let epsilon be positive, a given positive real number. And then when it comes time for you to deal with this statement, you're going to say choose delta equal to epsilon over 2. And then you're just going to go from there. How do you deal with this? You say let x be a given real number. Then you say, suppose this happens. And then you're going to try to prove that this happens. So I claim that by choosing your delta in this way, you will be able to prove that this is true. Okay, so you go ahead and write up the proof. In fact, it's not a very long proof, even though it looks like it's going to be complicated. It's actually just a few short sentences. But when you write up your proof, make sure of one thing. Make sure that you only write things that you know to be true. Don't write anything that you don't know to be true. Okay, so put your video on pause, and when you come back, you can have a look at my proof as well. Okay, so here you see my proof. It's entirely motivated by what I read as I go from left to right. So I start with let epsilon bigger than 0 be given. And now I remember I told you to deal with this statement by saying choose delta equal to epsilon over 2. Now we get to this statement. Let x be a real number. And now we're doing a direct proof, so we say suppose our hypothesis is true. Suppose that 0 less than absolute x minus 3 less than delta. Notice that I'm allowing myself to use simple math notation in my proof. I'm not writing everything in words. Now, I have to prove that this happens. So I put then. And now notice, I'm not going to write this, but rather I'm going to deduce it. I'm only going to write things I know to be true. I start on the left side and I write this. And that really is equal to this, if you just collect the 7 and the minus 13. And that really is equal to this, if you factor out the 2. But we've said that x minus 3 is smaller than delta, so that's really smaller than 2 delta, which is really equal to epsilon. So I put a comma, and I say, and so we are done, because I have really proved that this quantity is smaller than that epsilon. So I've succeeded in doing this. And you'll notice I never wrote anything. There's nothing written here that we don't know to be true. There's no wishful thinking in there. So it reads very easy for the reader. Now, the mysterious part of the proof is when you write that. Okay, so, but that's the logical way to write it. It's not the way that we came up with it. In fact, we came up with it by working in a totally different order. But you have to write up your proof in this logical way. And so that's going to remain a little bit mysterious for the reader when he or she first sees it, but they will understand when they realize that the proof actually works after that.